All right, this video is on linear operators. This is chapter 4 of Moon. Okay, so remember in chapter 3, we had the definition of a linear operator. So x and y are vector spaces. And then an operator that takes x into y is a linear operator if when we operate on, alpha x1 plus alpha 2 x2, that we get alpha 1 times the operator operating on x1 plus alpha 2 times the operator on x2. So this is what it means to be and this is for any x1 and x2 in X, and really this would be alpha 1 and f2 in the field F that is defined for the vector space. And I suppose that X and Y both have to have the same field. They can be different types of spaces, but they have to have the same field. So real numbers are complex numbers. All right, so in chapter 2, I guess this should be chapter 2, we had a number of examples of linear operators. So you may want to go back and look at the notes for chapter 2 on linear operators. And these would be different slides. Those refer to my PDF notes. All right, so given a linear operator, we can define now the norm of an operator. Before we had norms of vectors, and now we can start talking about norms of operators. So this is going to be a new concept for many of you. So this would be norms, maybe norms of a matrix, but you could think of also the norm of the convolution operator. Okay, so operators can have norms. There are different ways to define norms for an operator, but the most common is what's called the induced or subordinate norm. In other words, we define norms on operators by defining norms on vectors. Okay, so here is the standard definition for the norm of an operator. If you have an operator from these are two inner product spaces, x and y. Actually, these only need to be norm spaces to be able to define this. Then the norm of the operator is going to be equal to the supremum. So I'm going to take the supremum over the set of all x that is not equal to 0 of the vector norm. See, this is going to be the vector norm in y of a operating on x. So in other words, the linear operator A operates on x, so it operates on x and produces y. And we're going to take the norm here of that y divided by the norm of x. And we're going to go, and this particular norm is actually in the x space. So remember, x here is going to be, this is going to be in x, and this guy is in capital Y. Okay, it turns out that is exactly the same as taking the supremum of the norm of AX over the set of all x's on the unit circle, okay? And the unit circle would be defined in the appropriate norm. In other words, we're going to look at all, we're going to take all of the x's here, and we're going to see what the linear operator does to it. It might produce, maybe something that looks like this. So x, each of these x's map out through A, and then we would look at the largest norm. This would be the supremum over all of those x's. So different norms on A can be defined by taking different norms in x and y. All right, so let's do some examples. So if A takes L2 onto L2, then the 2 norm of A would be, you would take the supremum of the 2 norm of AX, that's going to be a function, divided by the 2 norm of x over all x's that are not equal to 0. And that's the same thing as taking the supremum over all little x's whose function norm is equal to 1 of AX. If we were to do the infinity norm of the operator, then we're just going to replace these two norms here, with L infinity norms for both the output space L infinity and the input space L2. Oh, this is a typo. Sorry, I've got quite a few typos here. If A is a function space from LP to LP, then we can define things in terms of the P norm. And we don't necessarily have to have an inner product. So it's the induced or subordinate norm, and the norm is induced by the vector norm. So again, the geometric interpretation, over here in my X space, I have the unit circle. And then A is going to map unit circle, it's going to take every point and it's going to map it to something. So as I sort of go in a smooth way around this circle, I might map out maybe a smooth function like that. And then the norm of AX on this side is going to be, the largest. When I take the supremum here, I'm going to take the largest of those elements. In this particular case, it would be a maximum. But the largest stretching under A would be basically the supremum of that operator. So when we talk about, for example, this would be the 2 norm of a 2 by 2 matrix. So this would be the 2 norm of A, where A is in our 2 by 2. And this would be the geometric picture that you would have for the 2 norm of a matrix. It's essentially the maximum gain of the operator over the unit circle. All right, norm of a linear system. So what is the system interpretation? So if I have this linear system where U of t goes in and Y of t comes out, then the norm of this system, this should be h of little s, is the maximum gain of the system. Okay, so another way you can think about that is, let A, so how would you compute it? So if A goes from L infinity to L infinity, in other words, a bounded input, bounded output system, if the system is bounded input, bounded output stable, then we can write the output in terms of its impulse response. This is the convolution of the impulse response with its input. And we can think of convolution, like we showed, as a linear operator. And so what is the infinity norm of that linear operator? Okay, so here's a little lemma. The infinity norm of that operator is going to be the L1 norm of the impulse response. In other words, it's the integral of the impulse response, the integral of the absolute value of the impulse response. Again, that's equal to the L1 norm of H infinity. All right, so how would we go about proving this? To prove, that the infinity norm is in fact equal to this the integral of the absolute value of the impulse response, we're going to do it by showing two things. One, that the norm is less than that value, and then two, that value is less than the norm of A infinity. Okay, so this is actually a general approach. We basically want to show these two things, and how we show them is relatively similar across these types of proofs. Okay, so the first thing we want to do is show that the infinity norm of the operator is less than or equal to this absolute value, or the integral of the absolute value of H. All right, so by definition, the norm of A is equal to the supremum of the norm of A operating on U, taking the supremum over all infinity norms equal to 1. So it's the supremum of all infinity norms equal to 1. And then what is a operating on u. It's the convolution integral. All right, so now we're going to start playing games. We've got an infinity norm on the outside, and now what we're going to do, and what the infinity norm means is that it's the largest value over all t, the largest absolute value. So that by definition, we get that that's equal to, this is equal to the supremum over all t's. So for t greater than or equal to 0, 0 to t, h of t minus tau, u of tau. Okay, now if we move the absolute value to the inside, remember if we have some function that goes, like this, the integral of this guy, we positive, negative, etc., it's going to be less than if we absolute value all of these, because we'll just get a bigger number when we move the absolute value to the inside. So when we do that, we have to use, less than or equal to, because moving absolute value to the inside means we're no longer subtracting anything, we're just adding stuff up. Okay, now if you were to take the largest, so this is going to be h of t minus tau times u of tau. Now if we were to take out the largest value, so in other words, I have this guy and it's multiplied, by something that does that. If we were to multiply by its largest value all the way across and then integrate, that's going to be larger still. So in other words, this absolute value is if we pull out the largest value of u. In other words, the infinity norm of u is just the supremum over all t of u of t. So we pull that largest value out, and now we'll get this thing, and it's we have less than or equal to. Okay, now we're taking the supremum here of all infinity norms of u equal to 1. That means this guy's equal to 1. So, we can go ahead and assume that that's equal to 1. And this is going to be less than or equal to, since this is the supremum for t greater than 0, if we were to go all the way out to infinity, then it's going to be less than or equal to the integral of h of tau. We've just done a change of variables here, t minus tau equal to, I guess this could be, we could think of this as now a sigma and a sigma, where sigma is equal to t minus tau. And what's this guy? Well, that's just the L1 norm. So we've shown now that, what we've shown is that the infinity norm of A is less than or equal to the L1 norm of H. Okay? So we've shown that guy. And we did it by just doing essentially a bunch of inequalities. This would be like a bunch of inequalities. All right, now what we're going to do is we want to now show that the infinity norm of H is less than A. And we're going to do that by picking a particular U that has norm equal to 1. So let's pick a particular U hat that's going to be 1 when H of t is bigger than 0 and minus 1 otherwise. And then you notice that, in other words, it's just going to, if the impulse response does this, then U is going to be, it's going to be, then it's, going to be like that. But notice that the supremum, as t goes to infinity, of the absolute value of U is equal to 1. So we know that the norm of U is equal to 1. Yeah, this actually should be, well, anyways, okay, so now the output is h of t minus tau, u of tau, and now when we multiply these things together, when it's negative, yeah, this should actually be h of t minus tau, and we're going to let this be ut of tau, like that. And, when we take the impulse response, we're going to end up with basically the absolute value of h of t minus tau. And so for this particular value, or choice of u hat, the supremum of h of t minus tau is for all t greater than or equal to 0 is going to be exactly, which is by definition, is by definition exactly the infinity norm of a u hat, and that's of course going to be equal to the integral from 0 to infinity of absolute value of h of t. And so by definition of the supremum, these two are equal, and that's less than or equal to the supremum over all norm u's equal to 1. There wouldn't be a norm u hat here. Because when I have a particular u hat, or a u hat, the infinity norm, is equal to this guy. And when I take the supremum over all u's, then, well, it just has to grow because I'm maximizing. So we have to have a less than or equal to. All right, so what did we do? We basically, we've shown that particular theorem, and our proof technique can hold for other operators. So essentially what we want to do is we want to show that the norm of an operator is equal to some number. We need to show that the norm is less than or equal to m, and m is less than or equal to the norm. And what we're going to do is to show that number one, here we show that the norm of ax is less than the norm of mx, and that means that when we take the supremum over all norm x equal to 1, then that's going to be since this guy is less than or equal to this guy, we have less than or equal to the supremum of norm x equal to 1 of m times norm of x. And now, of course, since we're taking the supremum when this guy is always equal to 1, then that's just equal to m. And then to show number 2 that m is less than or equal to the norm of the operator, we want to construct a specific x hat that has unit length and that achieves that value. And that implies that m is less than or equal to that, to the supremum over all possible values. And so we've shown that in fact the norm is equal to that value. All right, so that would be the general technique we go about to find the norm of an operator. And I'll have a couple of other examples a little bit below. Okay, so for any induced norm of an operator, we have the following. The norm of A operating on X is going to be less than or equal to the operator norm of A times the operator norm of X. And to prove that, okay, by definition, the norm of the operator is going to be the supremum over all X not equal to 0, norm of AX over norm of X. And so since X is not equal to 0, we have to have that the norm of A is bigger than, which is the supremum over all these guys. So it's going to have to be greater than or equal to the norm of AX over norm of X. And this is for any specific X. And now when we multiply norm of X on each side, we get our desired inequality. Also, for any induced operator norm, we have this submultiplicative property, where the operator norm of this composite operator A and B, so B is a linear operator from, let's say, X to Y, A is an operator from Y to Z, then the composite operator norm AB is less than or equal to the composite operator norm of A times the composite operator of B. And again, we can prove this as follows. So the norm of AB is going to be the supremum over all norm X equal to 1 of AB on X. And then we've already shown this guy, so we can basically, we do two different iterations of that. This is going to be less than or equal to, we think of that as X, and so we have the norm of A, norm of BX, and now we separate that guy out. And since we have the supremum of X equal to 1, this is always equal to 1, so that's actually equal to the norm of AB. Okay, and we have another definition. So we say a linear operator from x to y is bounded if the operator norm is less than infinity. So now we can talk about bounded operators, bounded linear operators. And the following three statements are equivalent. So we can talk about now continuous operators. We say that an operator A is continuous if if you have some sequence xn that converges to x star, that implies that when A operates on that sequence, we get this new sequence in y space that is A operating on xn. If that converges to ax star for all convergent sequences in x, so for every xn that goes to x star, we have that axn goes to ax star. And another way of saying that is for every epsilon greater than 0, there exists some delta, so that when x minus y is less than delta, so this is in the x space, that the ax minus ay is less than epsilon. This is kind of like this is the operator equivalent to defining continuous for continuous functions. So how do we define continuous functions? So here's t, and f of t, let's say f of t. What we do is we say, remember, a function is continuous at x naught. So f is continuous at x naught if, how do we do it? We said for every epsilon greater than 0, there exists a delta such that if x minus x naught is less than delta, in other words, we have this little delta ball here. So this would be, this delta, this would be x naught plus delta, x naught plus delta. So if x is inside of here, so if x is inside of here, then that implies that f of x minus f of y is less than epsilon. So in other words, you have over here f of x naught. So this is f of x naught. So if it's continuous, if a little delta ball on the t-axis gives you or I guess this would be your epsilon ball. So if you can pick any epsilon, so that when epsilon becomes small, when this here becomes small, it turns out that that the delta ball becomes small. So for continuous functions, something that's discontinuous, like this, you have for any epsilon ball, so I can pick maybe around this, around this point. I guess that would be like a circle or whatever. So around this point, if I pick an epsilon ball, I can't pick there's no delta ball down here, so that if I stay within delta, I stay within epsilon, because I can go arbitrarily close here, and now I jump outside of epsilon. So it's not true that for every epsilon there exists a delta, so that when x is close to delta, f of x is close. When x and x naught are within delta, that f of x and f of x naught are within epsilon. So this is the same type of statement here. When x and y are less than delta, that means that the operator on x minus the operator on y is less than epsilon. So this is a nice natural extension from continuous functions to continuous operators. All right, and then we have this beautiful little theorem that says a linear operator is bounded if and only if it is continuous. Okay, so the proof, it's if and only if. So if we assume that it's bound. So the first we show that continuity is a necessary condition, or I guess boundedness is a necessary condition for continuity. So suppose that it's bounded. What does that mean? That means that the norm of A is equal to m, which is less than infinity. And now we want to show that that implies continuity. So let xn be a convergent sequence with a limit x star. And then the norm of axn minus ax star, remember, we want to show if this thing converges, since we know that xn goes to x star. If axn minus ax star goes to 0, then we're done. Well, axn minus ax star, it's a linear operator, so we can pull the operator out and make xn and x star multiplied by the difference between xn and x star. And then we use the submultiplicative property to pull out the norm of A, and we have the norm of xn minus x star. Well, we know what the norm of A is. It's equal to m, and we know that, so this should be little x, that xn minus x star converges to 0. So that implies that axn minus ax star goes to 0, so A is continuous. Now we want to go the other way. We want to show that if it's continuous, it's also that implies bounded. So continuous is now a sufficient condition for boundedness. So we assume that A is continuous. That means for every epsilon there exists a delta, so that when x and y are within epsilon, that ax minus ay is within delta. So let's go ahead and pick an epsilon and a y. So if we let epsilon equal to 1 and there exists and y equal to 0, then we know that there has to be some delta, so that when x is less than or equal to delta, the norm of ax is less than epsilon, which is 1. Okay, so if we let x be some arbitrary number or some arbitrary vector in capital X, then when we multiply by this particular delta, so this is a number times x, the norm of delta times x divided by the norm of x. Delta times the norm of x is going to be a positive number, so we can pull that out. And then what we're left with is by the properties of a norm, we're left with the norm of x. And now the norm of x and the norm of x cancel, and we just get delta. So this whole thing is less than delta. So this vector here is less than delta. And we know that when it's less than delta, then the norm of ax has to be less than 1. So that implies that when A operates on this delta x divided by the norm of x, and we know that that is in fact equal to, by definition of the norm, delta norm x times the norm of ax, that has to be less than 1. And that implies by multiplying, multiplying to the other side, we get that the norm of ax is less than or equal to 1 over delta norm of x, which means, and this is true for every x, because we assumed, we picked x arbitrary. This is in, our capital X. So the operator has to be bounded, because when we take now the supremum over all norm x equal to 1, delta is in fact, or 1 over delta is in fact an upper bound. Okay, so we've shown now that the linear operator is bounded if and only if it's continuous. All right, Moon chapter or theorem 4.2. If A from x to y is a linear operator and x is a finite dimensional Hilbert space, then A is always bounded. So when x here is finite, then A is always bounded, which means it's always continuous. So we can always say that A, or bounded and continuity are the same thing. All right, so how do we go about doing the proof? So if we let the dimension of x is equal to n, then because it's finite, then we pick an orthonormal basis for x. So let P1 to Pn be an orthonormal basis, which means that we can write any x in terms of its generalized Fourier series, x with pk times pk. All right, now what we're going to do is let d be the maximum over, if we take the norm of a operating on P1, a operating on P2, all up to a operating on Pn. There's only n of them, so there'll be it's not an infinite sequence, so there'll be a maximum. So let d be the absolute maximum. Then let a operate on x and look at the norm. Okay, so we plug in, our generalized Fourier series. So a is going to, or x is going to be the sum of the inner product of x with pk times pk. And then we use the, so this thing is a linear operator, so we could write this as the norm of the sum of, x with pk times a operating on pk, and then we use the submultiplicative property to get to pull the sum out, but we'll have the absolute value of the inner product of x with pk times the norm of a pk. Now we know that this is again a finite sum, 1 to n, and we can replace this guy with its largest value as long as we use a less than or equal sign. So its largest value is d, so we get that this is less than or equal to d times now the sum of the absolute value of the inner product. And then you remember from Cauchy-Schwarz, the absolute value of x with pk is just the norm of x. It's less than or equal to the norm of x times the norm of pk. And remember, x is an orthonormal basis, so the norm of pk is equal to 1. And so this is equal to, d, and then we sum x n times, so d times n times norm of x. So we know that the norm of a operating on x is less than or equal to the dn norm of x, and that means that the operator is bounded, because if I were to take the sup of overall norm of x equal to 1, then that would be less than or equal to, and in here I would put the sup of all norm x equal to 1, and that's going to be just equal to d times n. So we know, this is the norm of a. So this tells us that that a is a bounded operator. All right, and which is what we were trying to show. If x is finite dimensional, then a is bounded. And we're done.